Welcome to Pearl, and we are looking forward to a very exciting day. So, our first Pearl Conference live session will be our panel discussion. So we made you aware on Tuesday in the email that we sent out that we had pre-released 3 videos: Planning to Fail with Reverse Psychology by Steve Heller, Transactional Graph Processing and Persistent Memory by Philipp Gotze, and Cross-Failure Bug Detection and Persistent Memory, Sihang Liu. So Steve, Philip, and Sihang, feel free to unmute yourselves. And I will moderate the discussion today, and I have some questions that we can ask as we go. But what we're going to do is, for those of you that may not have gotten to see the videos, or just to refresh your memory, we're going to have everybody do a quick summary of what they did. So I'll drive the slides. We'll actually start with Steve. So Steve, why don't you take 3 or 4 minutes to discuss what you discussed in your video, and give us an idea of where your focus is in programming persistent memory.
Okay, thanks. Hello, everyone. If you had asked me 6 months ago what I knew about power fail resilience, I would have been comfortable in saying that I knew how to spell it. Other than that, of course, I understood the general idea of grouping changes to a database into transactions that would be atomic from the point of view of the user, transfers between bank accounts being the canonical example. But I wasn't planning to add such a feature to the C++ library I was working on at the time, namely my 2 misses hash table for persistent memory. My focus there was on achieving the maximum possible single-threaded speed to retrieve records by key from a hash table of any size, and it was obvious that providing any type of power fail resilience would slow the program down significantly. Once I got my retrieval speed up to where I wanted it in late April, I was ready to go to market without worrying about power fail resilience. So how did I end up presenting a paper about power fail resilience at this conference? Well, our plans for commercialization were delayed while raising funds for IP protection. So rather than sitting around waiting for those plans to mature, I decided to take on the challenge of adding such resilience to my library in a wrapper so that the user could decide whether he wanted to pay the cost of resilience when creating or modifying entries in the hash table. This would enable 2 misses to replace the use of databases in cases where the user didn't need full SQL facilities, but just wanted to be able to access records by key very rapidly and still get power fail resilience. I then spent most of the next 4 months working on resilience and got it working on Linux via an undo logging approach. But for some reason, the same approach wouldn't work on Windows. In an effort to solve this problem, I built a minimal repro program and sent it to the wizards at Intel, hi Andy, to see if they could figure it out. After a lot of back and forth, and I'm sure a lot of effort on their part to reproduce the issue, they couldn't. We eventually came to the conclusion that it was my bootleg server configuration that was causing the problem. You see, up until now, this project has been paid for entirely out of my personal funds. This means I needed to get the most storage, at least 1 terabyte, for the least money, which involved a number of shortcuts. 1, putting 425 gigabyte parts on one socket, and 2, buying 3 250 gigabyte parts on eBay and putting them on the other socket. This resulted in an unsupported configuration violating Intel's population rules, which probably explains why the power fail resilience doesn't work under Windows. Although it doesn't explain why it does work on Linux. So I made plans to buy another server with a supported configuration. As soon as I get that server, I'll validate and if necessary, fix my power fail code. At that point, I'll have a hash table implementation that supports power fail resilience on both Windows and Linux without requiring users to worry about the details. And of course, if you're just retrieving data from the hash table, you won't have to pay the performance penalty for resilience. But to get back to how I ended up presenting at this conference, just about when I got to the realization that it's probably my hardware configuration that's the problem, I saw the call for papers for this conference and decided to make lemonade by doing a presentation on power fail resilience using my minimal repro program as a basis. Having explained that, I hope some of you are wondering, why is the library called 2 misses? The answer is that its design goal is to provide access to any record of any size in a hash table of any size without having to know in advance how big the hash table will be and without performance degradation during retrievals due to rehashing. The main limiting factor in retrieving records from a very large hash table is the number of memory references that are expected to miss in all caches, including the TLB. I call these memory references misses for short. The two misses library can in fact retrieve any record with a maximum of 2 misses, regardless of how many times the table has been rehashed, so it has met its design goals.
Thanks for that, Steve. I was actually going to ask you the first question of why you decided to focus on failure recovery, but you did such a good job explaining that. I'll save the other questions for a little bit, and let's move to Philip. Philip, why don't you talk, and then you can tell me when to advance slides. But why don't you give us an idea of the video that you presented as well?
Okay, then let's start. So I'm Philipp Gotze. I'm a PhD student at the Technische Universität Ilmenau from Germany. And we looked at the topic transactional graph processing in persistent memory in our database and information systems group. Next. Yeah, and first we looked at our preliminary work. So we did some PMEM-based data structures like B trees, LSM trees, and so on. And also on the persistent memory modules from Intel and what their characteristics are. And these you can see here on the left side. So we saw that PMEM has, for example, a higher latency, lower bandwidth than DRAM, and it behaves asymmetrically regarding reads and writes. And from this, we derived some general design goals, not only for our graph processing engine, which we developed, but also for other engines, storage layouts, and so on. So for the first two challenges, we thought, okay, we could, on the one hand, algorithmically save writes, and on the other hand, we could utilize a DRAM PMEM hybrid storage design, where we not only use PMEM, but also try to use a little of DRAM to hide the PMEM latency, and also to hide the higher write latency of PMEM. Yeah, the third part can be directly mapped. So this PMEM memory modules internally work on 256 byte blocks. So we want to optimize the access granularity regarding this. Then the fourth part is on failure atomicity or crash consistency. And we can only guarantee this for 8-byte aligned writes on current architectures. And we say that we should prefer these atomic writes instead of relying completely on logging and shadowing. Of course, sometimes it's not possible and you have to do something like this if you have bigger data. But if possible, you should prefer direct or 8-byte aligned stores. Yeah. The fifth and sixth are more like derived challenges. What we saw is that PMEM allocations are very expensive. So in one of the papers we saw it was I think 8 times slower than DRAM, although the latency is only 3 times slower. So we thought, okay, a countermeasure could be to use group allocations and reuse blocks instead of deallocating. So some kind of free space management. And the last point is dereferencing. This was also part of the persistent memory book from Steven Scargill, that if you use persistent pointers, the dereferencing can prevent optimizations from the compilers, as this is not integrated yet. So in the first place, we wanted to avoid dereferencing and use, for example, volatile pointers if possible. Yeah, then next. Next slide, please. Yeah,
Should be there.
From these, yeah. So from the general design goals, we derived then specific design decisions for our graph engine. And to quickly list them, so we had a linked list of chunks for our nodes and nodes, relationships, and properties of our graph engine. And it is cache line aligned and a multiple of 256 bytes. So the PMM properties, and we use a free space management. Then we have cache line sized records, or specifically they are equally sized, and this is necessary to address them via offset so that we can avoid this dereferencing. And also we have, for example, outsourced properties, and we use dictionary encoding also to allow these equally sized records. And the last point is that we have a hybrid storage model. This was a design goal number 2. that we utilize PMEM and DRAM, so to hide the PMEM latency, and this is currently implemented for index and transaction management. And as we call it, transactional graph databases, so what we use for a transactional approach is a multi-version timestamp ordering protocol. And you can see here a quick reference again, that we store on persistent memory only the current version and only one version, of course. And the rest is all in DRAM, so current active versions which are not committed yet, and also old versions. Yeah. Okay, next slide, please. Yeah. And in summary, so our contributions are the general design goals that can be used also for other storage designs or whatever you want to do with persistent memory. And for the contribution to the community, more explicitly, we provided 2 repositories, one with our PMEM-based data structures and algorithms on GitHub, and also our transactional graph database in persistent memory, which is called Poseidon, by the way. Yeah. And as a small remark, this is, of course, these are no products, this is educational work. That's why there are maybe some bugs, and we are open if you want to tell us or find something. Okay, then thanks for listening, and I'm open for questions.
All right, and before I go to Sihang, we'll ask you one question. Andy Rudolph, who's much smarter than I am, asks, your video mentions some possible NUMA optimizations in the future. Can you talk a little more on how that would work, such as how operations can be tied to a NUMA node?
Yeah, so for now we had only one pool. So we created the PMDK with one pool only on one socket. And this is, for example, already a problem because we utilize all the cores, so from both NUMA nodes. So currently we have 2. And we want to design at least that the chunks are maybe assigned. So we have a linked list of chunks that this is assigned to specific threads on this NUMA node. And because we already have a thread pool, we maybe could divide the thread pool in 2 parts per socket, in so many parts as we have sockets, for example. So this would be, or could be, an idea for this.
We have some other questions rolling in, and please feel free to continue putting those in. But what I'm going to do first, or do next, I should say, assuming it moves forward. There we go. Sihang, feel free to talk about your talk as well, and then we'll come back to the open panel questions.
Hello, I'm Sihang Liu from the University of Virginia. My talk was about cross-failure bug detection in persistent memory programs. So previously, Steve and Philip were talking about the programming side, and now I'm talking about the debugging side, which makes the program correct. Sorry about the phone. I guess it's kind of distorted because of the conversion. Hope it's already clear on your side. So testing software for persistent memory have a couple challenges. First, we already know programming for persistent memory is hard because there have been a variety of support, say the low-level primitives like CLLB and SFENS. And also using transactions may also be non-trivial because you have to understand how what the transaction provides and what the program logic do you want to implement. What's going to be dealt with during recovery, etc. So it is really hard to guarantee the program's recovery correctness. And so our previous work detects a bug during the normal execution. Say you perform a key value store insertion, how to make sure the procedure is fairly atomic, recoverable. And now in this work, we found that actually the recoverability also matters. The program stage after failure is very important because both stages need to work together. Say we call the normal execution pre-failure stage that has to really log things properly. And then in the recovery stage, you need to recognize those locations that has been logged and then perform the recovery, say unrolling the data that was messed up. So both stages are important. If one stage is incorrect, the software may not recover correctly. Next slide, please. And our solution is to reason about the execution correctness of both stages. So we have one stage of pre-failure, the other stage of post-failure, and we together reason about them together. In the pre-failure stage, we inject a couple of failures, and at each of the failure, we try to spawn a new program instance of recovery to recover from that failure, and then we perform testing during the procedure. The key idea of this testing tool, X-ray detector or cross-failure detector, is to understand whether the program is accessing any inconsistent location that was left over during the normal execution or pre-failure stage during the recovery. Say if you have something that's updated but not written back, and the recovery program tries to read from that and use it to recover the data, then it's certainly incorrect because the state of the data is uncertain after if things are not written back properly. So we have a couple of categorization on the type of cross-failure bugs. So if you have taken a look at the video, then it will be very clear, and also happy to answer questions about these two types of bugs. And if there's any detection of these inconsistent access, then we can report such a bug and locate where the bug happened and what is the access in the recovery stage or later execution that's trying to access buggy location. So our tool has found a couple bugs in Intel's code, most specifically towards the code regions that are during initialization, which people are overlooking because it's not the core functionality in the normal execution. I think that's everything.
Okay.
Should I pick some of the questions right now?
Yeah, sure. Well, I have one for you. I noticed in the video, one of the first things that you said is that it's important to have a meaningful state before and after failure. So can you elaborate on what a meaningful state is and why you say that?
So if I understand the question correctly, you mean the meaningful state, like so in the pre-failure stage, there's something updated, and what is a meaningful state? Is that right?
Right.
So we have basically two categories. So the higher requirement, let's just talk about higher requirement first, is some location regarded as a meaningful location as a program specification. For example, you have a couple logs during the transaction, and you may not delete all the logs in the previous log immediately. So a minimal state means you try to read something that is as your specification that is the latest log. You want to use it to unroll or roll forward, either way. Or another example is checkpointing. The database may have different checkpoints for the previous histories, and the latest checkpoint typically is regarded as a meaningful state, and the older ones should be discarded or be used if the latest ones are corrupted. So this is based on the program semantic level, which we call the consistency state of the data pieces, like the logs. And second level is about the actual location's status about persistence. So in the programming, at least in the normal ADR, we use a regular write and followed by a CLW and SFANS to make it persist all the way to memory, right? And there are a couple stages during this procedure. First, data has been modified, and we don't know whether it's going to be written back or not. So this is a somewhat an uncertainty state that you don't know what's the status. And then move on to next stage that you issue a CLW, but you don't have an SFANS to enforce the completion of the CLW. So this state we call it something as a write back trigger, but not written back. And finally, there's a CLW issued, which guarantees a SFANS issues guarantee the CLW to complete. So this is a persistent state. And the first requirement is already met. Then we look at the second requirement on whether data has been actually persisted. And both cases, if regarded by the program semantic or by persistence, both are satisfied the specification we said is meaningful. There's only one exception. That is, we call it benign cross-failure race, which is like a valid bit in the log. Say, I want to read the valid bit or some checksum and see whether the log has been persisted completely. And because the valid bit is a single char, a character, or a single 8-byte word, then so within the persistent atomicity granularity. So this is always regarded as meaningful because you always need to read from the location and see what is the status of the rest of the data structure. So it's a benign situation. So in summary, there are three types of situations. And if you satisfy all those specifications, it's regarded as meaningful. Does that answer the question?
Yeah, I thought that was very good. And Steve Heller, I saw you walking around in your video. I was actually going to ask you a very similar question because you had you made a similar point in your speech in terms of making sure that you have a good record of your transactions. So how would you answer the question that I asked? You know, what's a meaningful state, and how do you actually try to pursue or track the transaction so that you know, so that you can recognize either a bug failure or a power fail.
Okay, well, yeah, it turns out to be rather complicated to do that. Basically, what you have to do is, and I explain this in fairly great detail in my you know, the half hour, 25-minute, whatever it is, presentation. But basically, what you have to do is anytime you're going to make a modification, you have to, this is why I call it reverse psychology, which is actually a joke. It's not really reverse psychology in the psychological sense. It's thinking backwards. In other words, the question is, if the power fails, and I should have said between two lines. So let's say the power fails immediately before a specific line in the code. At that point, what information would you already have had to make sure was persistent in order that if the power fails at that point, when the program starts up again, it can say, oh, I can see I was here. And an example, there's a number of examples, and that's the sample code that I provide gives you an entire, you can step through it all and see what it works, see what it does. That makes it a little easier. But basically, in order to, let's suppose you're going to update the transaction count, which is one of the things I do, because I assume you have a batch of transactions coming in. You're going to handle transaction, and then the power goes out at some point during, we presume, during some transaction. So in order to tell which transaction you should start up again at, when the power comes back on, you have to know what the transaction count is, so that you know which the next transaction is, or the transaction you're working on right now is. The problem is, if you set the state saying, I'm going to update the transaction count, and then you update the transaction count, and then you have another state saying, okay, now I have updated the transaction count. The problem is, if the power fails between those two state changes, how do you know whether you have updated the transaction count or you have not updated the transaction count? Because there's no, you can't, however you subdivide it, there's always going to be a point where it could happen after the previous state, but before the next state. The way I solve that in my code is to keep an old transaction count and a new transaction count. So first I say I'm going to update the old transaction count, then I update it. Then I say, now I'm going to update the new transaction count, then I update that. Then I say, now I've updated both transaction counts. So with that information, you know that at any time in the program, the new transaction count should be one more than the old transaction count, unless it failed between the updates of the old and the new transaction count. And then you know that that's where it failed, and you can restart from that point. So it's really, really difficult to figure out what all the transitions of the states are that allow you to be able to recover the code, recover the program to the correct point. That's what makes it difficult to do this, and what's one of the things that makes it difficult.
Mm-hmm. Okay, thank you. Let's see, and by the way, there's quite a few questions coming in. If we don't get to all of them today, what we will do is we'll actually post a blog on the PIRL site where we'll have everybody answer the questions that roll through, but let's see how many of them we can get to today. So to fill up, there were a couple similar questions that come in on you place hot data in DRAM and in persistent memory, and so it talks about the fact that it's cached in both places. One question would be, what percentage of memory accesses in the transaction hit PMEM, and the other portion of that was how do you manage the transition between the two?
So actually it's not, I wouldn't call it like caching in DRAM, because we kind of prepare it in DRAM. So if a failure happens during a transaction, it's never touched PMEM. So this is just an optimization that inconsistent states are not written to PMEM, only at the commit stage. Yeah. Regarding the percentage, I would say it really depends on the workload, what you have. So if you have so in the presentation, I don't know if I mentioned it, if you write or if you insert something new, then you directly write to PMEM. But if you update, you first do it in DRAM. So if you have a lot of new data with inserts, then of course your access rate to PMEM would be much higher in the beginning. Unless, so also not only at the commit stage, but also before. And if you have updates a lot, then the percentage will be maybe 50-50 because we have to first access DRAM and then later copy all this to PMEM. Yeah, that's why I would say it mainly depends on the use case, what you or which data you use underlying this graph engine.
Yeah,
and
okay.
regarding the management, I don't know what exactly, let me think. So it's a management between hot and cold data. This is the question.
Yeah, how do you manage the between the hot and the cold data?
Yeah, as I mentioned, so I wouldn't say, so currently I don't think that it is hot and cold data, only that, okay, maybe you could say this. So if the current version or most recent version, this is the one in PMEM, so that's actually the hot data, I would say then. And older versions, which are already committed, these are the cold ones. I would say, so they are currently in DRAM, but we also thought that maybe for time travel queries, we could also move them to SSDs, for example, instead of keeping it all in PMEM DRAM. But currently it's implemented like that the most current version is in PMEM and older versions and also uncommitted versions are in DRAM. And if there's not enough space or after a time, the garbage collector kicks in and also removes older versions, which are not visible or not touched by any active transaction anymore. Yeah. So this is how it is currently managed.
Okay, excellent. Let's go to a question for Sihang. If my data structure is designed in a way that no specific recovery is needed, but the read will tolerate the inconsistent state and correct it on the read path, can the XF detector help?
That's a very interesting point. I think what you're assuming is something like a structure that doesn't require recovery, but something like self-validate or use atomic pointer updates to switch the different versions. So in that case, I think XF detector can still help with some extension. So right now we focus on the transaction from PMDK and something low-level programming based on the PM. But if you have, I think your solution is based on, so let's just say based on some atomic update on the pointer. So you can determine the latest version without needing to roll back something. Then there could be still bugs, obviously. Something like the pointer is pointing to the wrong version, for example, or it's the pointer switch is say is not within the atomicity granularity, for example. So in this case, XF detector can still really can still tell the problem. Let's just say if it's pointing to the wrong version, then you can, so XF detector using a versioning mechanism. So we assume the latest version is always the one you want to use for the consistent copy. So we can tell whether this is the latest version or not the latest version according to the sequence of updates to the logs and I guess the data structures and to the specific pointer in the switch. So if you have other mechanisms that you mentioned, just let me know offline. Also,
Okay.
I think the other case is say you use some recovery mechanism just built into the data structure, like using a checksum to recover. Then this can also be told by the XF detector because those two versions need to match, and they have to belong to the same epoch or same period updates.
Okay.
I think that answers the question.
Yeah, I think so. Let's see. I saw one for Steve come through, and I had a similar question. Let's see if I can merge the two together. The question from the question on the chat is, if I have a supercapacitor, so the system has some number of milliseconds from power failure to the actual loss of internal power, how much of the efforts can be of the efforts that you were doing could be replaced with similar solutions? And I'd follow that up with, and you made a complex solution to try and to try and be comprehensive. How is there a back off point where you could say, well, I can make some assumptions and move to a simpler solution to try and have less of a performance impact?
Yeah, well, I do discuss this in the the big presentation, and that is if EADR is available, then most of these things, well, then the Intel library, I'm using PMDK to do the actual flushing and so forth. If EADR is detected by PMDK when it starts up, then flush turns out to be a no-op. So then all of the work that requires the data to be flushed to persistence will take no time, because the PMD, or almost no time, because the PMDK library, when I say pmem persist or pmem drain, or whichever one is being used in that case, will just say, oh, I'm done, there's no problem. So that the part that relies on, the part that requires things to be flushed, so that you know that the things you have written to the persistent memory are really written to the persistent memory, will be much faster and easier. However, you still have to know, unless you have something similar to the old days when I started programming, where we used core memory, and a power fail resulted in a non-maskable interrupt where the registers were flushed to core, and then when the power came back up, the registers were reloaded from core, including the instruction pointer, and everything continued from where it was. If we have that, then you don't have to do any of this stuff. You can use you don't have to worry about the persistence at all. But until we have something like that, you still have to know when the power went out, where were you in the process, what transaction were you at? So you have to keep track of the transaction count. Had you already updated the old transaction point or whatever? All these counter, all these things have to be kept track of. The difference is that the performance implications will be much lower, much smaller. The performance hit will be much smaller than it is now, because the flushes will not have to actually be physically done by PMDK. So you could still use the same method, but you get the same, you wouldn't have the speed interference.
Okay. So Philip, we already talked a little bit about NUMA optimizations, but I actually wanted to also ask you about multi-threading. And this comes from the first time I saw Andy Rudolph present how to program persistent memory. The example that he used was actually, let's first multi-thread it, and then let's make the memory persistent. And he showed how the mechanisms were very similar. So you mentioned that multi-threading was particularly useful for persistent memory. Can you elaborate on some of the similarities and differences that you found in terms of enabling your program for both multi-threading and persistent memory?
Jim, it appears Philip may have dropped off of the call and has not re-entered the lobby yet.
Okay. Well, we'll have him answer that question in a little bit then. This is a live virtual conference. It's also fairly late for Philip. You might have popped off for a brew. Sihang, I saw a question on the chat for you. If one accesses a persistent location with no transaction or persistency barrier at all, is that something that your code can detect?
Let me just rephrase the question. If one access, so I think the question assumes there's no transaction being used, use libpm directly. And the program doesn't have any barriers. So I think this case can still be detected fundamentally. Let's just assume your program is still somewhat a program for persistent memory. You have a stage during the update. You also have a stage in the recovery, presumably. And there's no fence whatsoever during the program execution in the, let's just say, the pre-failure stage in the update. So the failure injection will still put a failure anyway to the end of the program. So in that case, when we look at the program's update, okay, there's no fence at all, no barriers, and no transaction support whatsoever, then essentially every update will be accessing an inconsistent location. So I think it can still be detected.
Okay. I think that, and I think you answered it. The clarification was like someone who forgot a transaction. And I think that's what you covered. So Philip, I think I saw you come back. I'll ask I was asking a question just as you dropped. I was asking about multi-threading, and you noted that multi-threading was particularly useful for persistent memory programming, and Andy Rudolph in an earlier presentation that I've seen mentioned that programming for multi-threading and programming for persistency are very similar. So can you elaborate on some of the similarities and differences of enabling for both persistent memory and multi-threading, and how easy you found moving back and forth between the two?
So sorry, I just rejoined. I missed my internet went wrong.
Oh, you're fine. At least your dog wasn't barking.
Okay, can you repeat the question, because also my audio is switched off. That's why I had to.
Sure. So just mentioning about multi-threading, you had said that multi-threading was particularly useful for persistent memory programming. And so can you elaborate on some of the similarities and differences between programming for multiple threads as well as programming for persistent memory?
Multi-threading, so our previous data structures, I have to admit, we hadn't done that much of multi-threading, but for the graph engine, which was actually done by our professor by himself, we invented, or we did a thread pool, so which also works with thread local variables and so on. And so the only problem with PMEM is the bandwidth, but yeah, if we have a lot, or if we have interleaved of these together, then we can achieve a good performance. But I don't think that I think that bandwidth is a bottleneck here. And maybe it gets better over the time, but currently I guess that in DRAM it scales a bit better. And I think we can also see it with, I think Steve Swanson has also this benchmarks where we saw that it quickly goes down the performance. And there's more for writing, for example, I think for 2 or 3 threads, that it actually is a peak where we reach it. Yeah.
Okay, very good. I saw a question for Sihang come through. Your system seems to most directly apply to low-level programming. Can you talk about what's relevant for some of the for programmers who are going to use higher level libraries like PMDK, and or more detail? The example and the evaluation showed PMDK, but your examples were at a lower level. So can you talk about how your work can operate at some higher levels?
Our tool is fundamentally, we detect these low-level things, like what is the relationship between reads and writes across 2 stages, and how does the fence and the write-back fence apply to memory locations. But the library is essentially a collection of those instructions, so the low-level primitives. So what we did for if you have a chance to take a look at our main paper, we embed these low-level things to the annotations to the library, so we can keep track of when the transition starts and when transition ends, and locations are regarded as consistent according to the transaction semantics. So basically, by embedding these annotations for, say, something marked as always safe, like provided by Intel, or something marked as a commit variable, those things embedded into the PMDK transaction, we can detect automatically. And for low-level programming, there's a need for annotation on these primitives that are, say, benign cross-fit arrays, because it's hard to tell whether some location is a commit variable or not.
Okay.
I guess I can also follow up on Stephen's question about that annotation part. Can I go ahead?
Yeah, go ahead.
So the question was about how to automate the detection which races are benign. I think it's very related to this question. So for now, we require annotation because it's hard to tell from the program semantics alone. But we think it's possible to use some sort of compiler technology and some profiling to determine what locations are supposed to be regarded as those commit variables that has to be benign. For example, in the recovery program, it's a typical way to read from a value bit and see, okay, the value is 1, you use a log. If value is 0, you don't use a log. You keep the in-place updates. So these patterns are somewhat fixed. So it's possible to use a compiler pass plus a a profiler to tell which locations should be regarded as benign races, because those are frequently accessed during recovery and used to determine the correctness of other locations, I guess consistency of other locations.
Okay, that makes sense. So Steve Heller, talk a little bit more. You talked about identifying the necessary data to successfully restart a transaction that was missed due to a power failure, and so and you actually had a fair amount of insightful comments that you made during your larger presentation. So I just wanted you to elaborate on that briefly. As a programmer for developing for persistent memory, how much time or how much effort do you recommend people put into thinking through some of the failure recovery and what data they need to be looking for in order to do so?
Well, the first thing I would say is, if you don't have to do it, don't do it. It's a lot of work. It's very hard to test because you would, in order to really test properly to get 100% testing, aside from the things that I just found out about today, up till today, I didn't really have any way of doing it other than saying, let's just turn the power off while the program is running. And I know that there's going to be, I believe there's another presentation by Terrence Kelly and his partner in the power fail material.
Yeah, that's next week.
Right, that he talks about this. So basically, what you'd have to do is you'd have to be able to cut the power off at a particular time. And you can't even do that at a particular line in the code because the caches are going to be flushed. I mean, you don't know, to some extent the caches may be flushed. You don't really know exactly when the power is going to go out. So that's very difficult to test. So I would say the first thing to figure out is, do you need to do it at all? If you can use PMDK transactions, then you should very seriously consider doing that. If you can use another persistence or power fail resilience mechanism, I suppose a SQL database, if those actually pass the power fail testing, which is something that Terrence has written on extensively, which they don't necessarily do, then you could do that. Or if you just need a hash table, you can use my hash table, which now I'm going to do some re-engineering of, I believe, with respect to keeping stuff in non-persistent memory in DRAM. Right now I don't do that, but I can keep everything in DRAM for an update until such time as it's going to be made persistent. That was a very, very helpful suggestion, and I'm going to take a look at that to see if that will help, that Philip mentioned. But basically, it's very difficult. It's difficult because it's a weird kind of thinking. It's weird in sort of the same way, an analogous way to the way multi-threading is, which I found to be not at all helpful or useful in my application. I tried doing multi-threading in a fairly simple way, and the performance was terrible because the thread switch takes a lot longer than the persistent memory access. So you end up with very, very poor performance if you do that. What I did do is do prefetching. Prefetching is extremely helpful if you know what the next thing is going to be. Even if the prefetcher, the hardware prefetcher won't help, you can still do that. So basically, you shouldn't do it unless you need to do it. You should do it only for those things where it is absolutely imperative that it should be able to be restarted successfully, like financial transaction data. I mean, if you're just doing a bunch of reads or you're doing something from a transaction file that you can input everything, the performance hit is horrendous. It takes, in my program, it's something like 50 times as slow to do all this overhead to guarantee the resilience as it is if you don't care about that. So you should very carefully determine what parts of your program need it, what parts of your data need it, and only apply it to those places, because it's very, very bad. Unless you have EADR, in which case I don't know, but it's probably not very bad. I'll test that as soon as it's available.
Okay. Let's see, Philip, I'm gonna try and put a couple of questions together. And it actually goes to there's a broader question, and I'll ask all three of you. So I'll start with Philip. The question was, you build a variety of different data structures, and what's the most surprising thing that you found that's easy or that's hard through that process? And I'd open it up a little more. What have you found that's easy about programming persistent memory in general, and what have you found that's hard?
So from my perspective, if we start with the easy part, I was quite surprised how easy it is to use or to program persistent memory if you use PMDK. So although it was a switch in thinking with persistent memory, I found it quite natural to use PMDK. So this was for me the easy part, or quite convenient part. But the hard part was if you wanted to do some things manually and use the CLWB and SFENS instructions. That was something which I never did before, because I'm more from the database part and I don't use assembler that often. That's where it was kind of hard in the beginning for me. Okay, what actually has to happen and what does the CPU do? Because I think I had one lecture about this in my studies, and then I never did this assembler stuff again. So this was kind of a hard part. And yeah, and maybe another hard part, or which I couldn't think of in the beginning, was our 6th design goal. So this dereferencing, I think this was also a question I found here. I never thought this in the beginning, because I was used to that the compiler is able to optimize dereferencing and all this stuff. And there I was kind of confused why it was so slow. And then I think Ismail Okit, maybe some people know him, told me that you have to avoid this dereferencing because I was doing it in the loop, always dereferencing part from the from persistent memory and then accessing the next entry. And when I just did the dereferencing before and assigning the virtual pointer or a virtual reference in this case, and then in the loop I always use only this reference, then it was much faster. So I couldn't think of it in the beginning because I was thinking the compiler was optimizing it before all the time. So this was something new.
Excellent. So Sihang, I'd ask you the same question. So what do you find about programming persistent memory that's hard and easy? I mean, what's surprising to you, or what do you find remarkable?
The easy part first. I guess the easy part is if you use PMDK transactions, there isn't much work involved. Although it's still more difficult than using, say, C++ standard library. But it's not too big a deal, I would say. At least I could pick it up very quickly. But the hard part is to use those low-level primitives to design very efficient data structures, like customized data structures. This is really difficult because as a program, I have to design all these low-level features, like how to design log, how to use the as a recovery program, etc. Like, there's nothing available yet, and this is the part that really comes where bugs come from.
Okay, so I'll go to Steve Heller for the next question. But again, you know, generic. So Steve, if somebody says I'm new to persistent memory programming, what advice would you give them to get started?
Well, the basic thing is, if you don't care about performance, it's easy to do persistent memory programming. But if you don't care about performance, why are you doing persistent memory programming? That's the difficulty. Basically, what is, I mean, it's sort of the same question, what's easy and what's hard. If you just think of it as memory, and you just say, well, I have a lot more memory. I have all this address space that's like memory, and I can store all my data in it, and I can write my programs the way I would normally write them, and just say, well, it's just like memory, or it's just like storage, it's just like a disk or an SSD, but it's a lot faster, so I can access a small piece of data quickly. The problem with that is that it turns out that, unlike in database programming, where you don't care how efficient your memory accesses are in your program, because if you have to do one database access, that takes thousands or tens of thousands of times as long as it does to do a memory reference. you have to invent. I had to invent. I hope other people won't have to do this. I had to invent a new style of programming in order to get maximum performance from persistent memory, because it turns out that if you add one extra memory reference in your program and everything else is the same and you're accessing persistent memory, that can slow the program down. And I mean DRAM reference, not a PMEM, but a bad a DRAM reference, a miss in all the caches, that can take 150 nanoseconds or 200 nanoseconds when you have to reload the TLB and so forth. So that's very, very slow. And that can kill your performance. That can reduce your performance by 30 or 40 or 50% compared to what it would be without that one, or 20% compared to what it would be without that one memory reference. So you have to merge the issues of database programming, which is minimizing references to storage, and in-memory programming, which is minimizing the amount of processing you do. Sometimes a divide makes a difference. Sometimes a divide is noticeable in how long the program takes. Usually it isn't, but we're talking about tens of nanoseconds. So it's very, very difficult because you have to take into these consideration all of the things you have to worry about in database programming and in memory programming.
Okay, good answer. Philip, I'd ask you the same question. What advice would you give to new persistent memory programmers? You have to come off mute.
Sorry, thanks.
You're good.
Yeah, I would say to start at the very high level. So this is what I found easy, as we talked in the beginning, that these PMDK transactions are very straightforward. So I would also recommend to start with these and to see how everything works, and that everything is consistent in the end. And then afterwards start to dig more into detail, where can I improve performance, and then see, okay, maybe this transaction, to put it around all my operations, or all of this, or every part of my operation, is maybe not a good idea. And then maybe you start with, okay, how can I make it smaller, the transaction part, or which data is part of the transaction, and then maybe later decide, okay, I can do my own PMEM drain and PMEM persist and find the real fine tuning. So I would say always start at the highest level of abstraction and then go lower as you need it.
Okay. So Sihang, I'm going to come to you, and I'm going to try and come to all three of you with this last question, because I'm curious. And I say this as a geek. You can't spell geek without double E. My one degree in college. The three of you are a lot smarter than I am, and you've seen opportunities for different technologies. There's thread optimization. You could focus on network efficiencies. You can focus on security. But instead, the focus of all three of you has been on persistent memory. So Sihang, why did you choose persistent memory? What attracted you to programming persistent memory over all the other really cool technologies that you can play with out there?
So a very short story. I was exposed to persistent memory when I was doing the undergrad at Michigan. Had a chance to use the emulated persistent memory. And then once persistent memory is released by Intel, I started using it myself. Actually, I bought persistent memory for my own server. I just wanted persistence everywhere, not only on the disk, but also on the memory DIMMs, because I think having the persistent memory is really a way to accelerate all those storage technology, storage systems. And this will be the future, I believe, that's unifying the memory and storage, which I believe unification is always a trend in many areas. I think that's kind of the overall motivation behind that's trying to push me towards this direction. I feel this is really exciting to me.
Excellent. And Philip, same question to you. What makes you geek out over persistent memory?
I think it was more random, because in the beginning I had a different PhD topic, to be honest, and I wasn't quite pleased with it. And then the professor already wrote a new proposal where he wanted to utilize or look more into detail about PMEM. And then I was quite interested in this, and was kind of not begging, but kind of pushed myself into this so that I could work on this, because I found it kind of interesting to have this combination, not only to do software, but also to really think about low-level hardware, what actually happens there. So I found this, this mixture very interesting.
Excellent. And Steve, we don't have a lot of time left. We only have about 30 seconds, but especially, you've been doing this stuff for as long as I've been alive. And so I'm curious as to what attracts you now to persistent memory.
Well, this is the ultimate performance thing. It's the fastest thing you could ever have, and right now, technologically speaking. And I wanted to build the fastest hash table that anybody ever saw for this fastest type of storage that anybody ever saw. And as soon as I heard about it, I said, wow, I got to get some of this. I bought the first server with persistent memory capabilities that the company that sold it to me ever sold to anybody last April, as soon as it was available. I just said, I've been waiting for this for 50 years. Now's the time.
Excellent. So there are some other questions on the chat. We will save those, and what I'll do is I'll follow up with 3 of you afterwards, and we'll do some blogging answers to the questions.